Okay, now we're going to venture into slightly more complicated problems that actually treat the real case of donors at arbitrary temperatures, donors and acceptors at arbitrary temperatures, as well as cases where you may have both. And so first, we've looked at the Fermi-Dirac distribution, which is what applies for carriers, electrons in the conduction band, or holes in the valence band. So we called this f of e. So it turns out that the analogous function for donors, which we might denote like this, although there's no real established convention, looks slightly different. So the bands use this function 1 over 1 plus exponential of e minus ef over k bt. And in the case of donors, you have a slightly different expression, which has a little factor called the degeneracy factor that comes before the exponential. And in this case, you use the energy of the donor minus EF over kBT. So when we're using this expression, it's important to note that the donor energy ED that we're putting there is not the ionization energy, but rather the energy on an absolute scale. So this is ED here. Let's say our EF is somewhere down here. Here's EC. Here's EV. And so this would be the ionization energy here, and we'd give this as EC minus ED. So this is a factor of 1/2 for donors, and the analogous expression for so donors for holes, it turns out you put a factor of 4 right there for most semiconductors. So this changes things slightly. Essentially what it does, remember when we were talking about the Fermi-Dirac distribution, we showed that it reaches 1/2, the value of 1/2, exactly at the Fermi energy. This little degeneracy factor for the donors will shift that point ever so slightly. If you look at the exponential, if we're looking at a distribution of donors, it just means that the distribution will not equal 1/2 exactly at the ED energy. Okay, so in order to figure out what happens in the semiconductor as a function of temperature, let's say, we need to go back to our basic equation, the charge balance. Or charge neutrality. And we want to think about all the different types of carriers. So there's going to be some holes in the valence band. There's going to be some electrons in the conduction band. And then there's going to be a third charged entity in the system, and that is the ionized impurities, or the ionized donors. So if you put in a quantity Nd donors at any arbitrary temperature, some fraction of them will be ionized. It turns out at room temperature you can basically assume that's 100%, but if you go down in temperature, that is no longer a safe assumption. So our charge neutrality expression would simply sum up all the positive charge things. So we have the quantity P plus Nd plus, and that's got to equal the negative entities, which are simply the free electrons. Then we substitute in all of our expressions. So we can substitute in the so NV exponential, and I'm just going to quickly do this, so I'm going to just put parentheses for the argument there. So the ionized fraction of the donors are going to be donors that do not have electrons. So this expression is the probability that it does have an electron, or that the state is filled with an electron. So we have to do 1 minus this. So to get Nd, we do plus, so Nd, the total number of donors, times 1 minus 1 over 1 plus 1/2 exponential to Ed minus EF over KBT, and then all of that is going to equal NC exponential of the argument, where this is a negative EC minus EF, and over KBT. And here we have negative EF minus EV over. Okay, so we can manipulate things, and the book goes through and actually does this example, but in the end you end up having to solve for the position of the Fermi energy in order to self-consistently solve this charge neutrality equation. In some cases, it's possible analytically to do this. So, for example, in the case we just laid out, where you have just some ionized donors and some electrons as the majority carriers, and then some holes as the minority carriers. And it turns out it's a little bit of an advanced topic. In this class, we're going to use the assumption that everything is ionized most of the time. But I think it's worth mentioning in these problems to find the concentrations of electrons and holes as a function of temperature. If you make some substitutions, so if you define some variables, let's say x, we're going to define as exponential to the EF over KBT. And then you recognize that terms like this that have like if you see a term exponential to the minus EC minus EF, for example, over KBT, you could actually write this as a product of two exponentials. So this would be exponential to the minus EC over KBT, and then you got a minus sign distributed over to the EF, which becomes a positive. And so instead of writing out that whole thing again, we just pop in the X there. So if you start making substitutions like this, what you'll realize, this factor here, minus exponential minus EC over KBT, that's actually a constant. It's just a numerical constant. So the structure of this equation, if you make this substitution up here that we started with, actually turns out to be some sort of a polynomial function in this new variable x. And so you'll get something like c1, like c1x plus c2 goes on to equal 1 over x. You get some expressions like this, and then you can manipulate things around, and eventually sometimes you even end up with some squared terms here. So if you have three types of carriers, you're going to get a cubic equation. If you have three types of charged entities in the system, you'll get a cubic equation. And if you get four types of carriers, let's say you had donors and acceptors and electrons and holes, you'd get a quartic equation. And then you have to go back to your algebra skills to solve these symbolically first, and then you can solve for all the quantities. So the number of times you'll probably have to do this in a career are pretty small unless you're a specialist, but I do think it's handy to know where these solutions come from. So let's talk about some other behaviors here. I mentioned the case of a compensated semiconductor, and this is going to be the most general case that you would run into, so something that has both donors and acceptors. So we're going to have our conduction band, our valence band. You have your free electrons, you have your free holes, and then we're going to have some acceptors, Na, and we're going to have some donors, Nd. We're going to assume that Nd is bigger than Na, so we've still got an N-type material. But what's going to happen is the effective number of donors that will contribute to the N, the free carrier population in the band, is actually going to go down. So in order to minimize their energy, for each acceptor, one of the electrons from one of the donors will drop down and fill that state. So remember that electrons like to fill just like water in a bucket. They'll fill from the bottom up. And so if there is an empty state, an acceptor does represent an empty state for an electron, it'll drop down there. And so our net number of donors that are available to be ionized into the conduction band is now going to be Nd minus Na, and that's our net doping. And then we can define something called the compensation ratio, which is just, usually it's given the symbol K, and that's defined as NA over ND, in this case where it's a net N-type. Of course, that compensation ratio would be ND over NA if it was net P-type. So the charge balance in this case is a little more complex, and I'll just write out the charge balance equation. So we're going to have the N plus NA, and because of what I showed, where the electrons from the donors will drop down and fill all of the available acceptors first before going up into the conduction band, we know that all of the compensating acceptors will be ionized all the time. So that means we don't have to worry about their statistics. We just say that they're 100% ionized. So that means that they're Na minus. So that's the left-hand side, and then on the right-hand side we have the whole concentration P plus ND plus and we can then make the substitutions, and some good analysis has been done over the years, and I'm going to show you the results instead of dwelling on how to do it. So if we plot the carrier concentration N on a log scale as a function of 1 over temperature, we'll see a few regimes of behavior. So at very high temperatures, so 1 over T, very small means very high temperatures, we'll have the carrier concentration dominated by Ni. And then over a pretty wide range of temperatures that usually is designed to include room temperature, our net concentration would be given by Nd minus Na. So over this range of temperatures here, we can assume full ionization for the donors and the acceptors. And then finally, as you go colder and colder and colder, that means 1 over T is getting larger. Eventually, some of these electrons from the conduction band are going to fall back into the so-called freeze out into their sort of home donors, and the process again is called freeze out. So if you let's say you made a microelectronic circuit and then you tried to fly it on a satellite, you'd have to be careful that your electronics would still work at that temperature. It turns out that there's two slopes, and the reasons are given in the book here, but the half slope region and the full slope region. So the full slope region gives you the ionization energy of the donor. So it gives you EC minus ED, and the half slope region gives you EC minus ED divided by 2. And interestingly, this crossover, this kink here, can be shown to occur at the concentration of the compensating the compensating acceptors. And so another way to look at this physics here is that you could use the point at which the freeze-out switches from half slope to full slope in order to identify your amount of compensating acceptors. Okay, so in general, the excuse me. In general, all problems having to do with carrier statistics can be approached from writing this charge balance equation and then substituting in the appropriate expressions. One more substitution you can do is remember that if this is an n-type material, you could, instead of writing out the full expression for P, you could substitute in Ni squared over Nd, for example. Although it's not always the wisest to do that in complicated situations. In most simple situations where you're in this regime where you can assume full ionization, everything works fine like that.